What NASA isn't telling you about the Sun's mysterious heart. Part 1. Birth of the Sun and Nuclear Furnace Origins. The Sun, our life-giving star, began its luminous existence approximately 4.6 billion years ago, coalescing from a vast, swirling cloud of gas and dust. This immense interstellar nursery, primarily composed of hydrogen and helium, slowly began to collapse under its own gravitational pull. As the cloud contracted, its central region grew denser and hotter, a primordial core forming amidst the cosmic dust bunnies and sparse atomic particles. This gravitational collapse was the initial spark, a slow, majestic dance of matter drawn inward, setting the stage for the fiery birth of a star. The increasing pressure and temperature within this nascent core eventually reached an unimaginable threshold. At this critical juncture, the hydrogen atoms, once free-floating, were squeezed so tightly together that they overcame their natural electrostatic repulsion. This extreme environment ignited the most fundamental process in a star's life, nuclear fusion. Hydrogen nuclei, under immense duress, began to fuse into helium nuclei, releasing an astonishing amount of energy in the process. This wasn't merely a chemical reaction. It was a fundamental transformation of matter into pure energy, as famously described by Einstein's E=mc². This fusion reaction transformed the collapsing cloud into a true star, a self-sustaining thermonuclear furnace. The outward pressure generated by this incessant energy release perfectly counterbalanced the inward pull of gravity, establishing a state of hydrostatic equilibrium. It was at this moment that the proto-sun truly came alive, no longer just a hot, dense ball of gas, but a shining beacon. The light and heat we experience on Earth today are direct descendants of these initial, violent, and ultimately stabilizing fusion events deep within the Sun's heart, a process that continues without pause. The energy produced in the Sun's core is phenomenal, equivalent to billions of hydrogen bombs exploding every second. Yet this incredible power is released in a surprisingly controlled manner, maintaining the star's stability over billions of years. Without this continuous fusion, the Sun would rapidly collapse back under its own gravity, its internal pressure no longer able to resist the overwhelming inward force. Understanding this delicate balance between gravitational collapse and fusion's outward push is key to comprehending not just our Sun, but stars across the universe. The raw materials for this grand stellar alchemy were inherited from previous generations of stars. The hydrogen and helium present in the original nebula were not entirely pristine. They contained trace amounts of heavier elements, forged in the hearts of long-dead stars and dispersed into space by supernova explosions. This cosmic recycling means that the very atoms that make up our Sun, and indeed ourselves, have a lineage stretching back to the earliest moments of galactic evolution. We are, quite literally, stardust, intricately linked to the Sun's ancient and powerful origins. Part 2. Layers of fire. Core, radiative zone, convective zone. Beneath the visible surface of the Sun lies a complex and dynamic internal structure, a layered inferno, where energy generated in the core embarks on a long journey outwards. The innermost region, the core, is the engine room, extending about 1/4 of the way to the surface. Here, temperatures soar to an astonishing 15 million degrees Celsius, and pressures are 250 billion times greater than Earth's atmospheric pressure. It is within this extreme crucible that nuclear fusion reigns supreme, converting hydrogen into helium and releasing the immense energy that powers our solar system. Surrounding the intensely hot core is the radiative zone, a vast shell approximately 300,000 kilometers thick. In this region, energy generated in the core is transported outwards, not by the movement of matter, but by photons, particles of light. These photons embark on an arduous and incredibly long journey, repeatedly absorbed and re-emitted by the dense plasma. A single photon can take tens of thousands or even hundreds of thousands of years to navigate this labyrinthine zone, bouncing randomly in what is known as a, quote, random walk, before it finally escapes into the next layer. Beyond the radiative zone lies the convective zone, which extends from about 70% of the way out from the sun's center to its visible surface. Here, the plasma is cooler and less dense than in the radiative zone, allowing for a different mode of energy transport. Hot plasma rises from deeper within this zone, carrying energy with it, much like water boiling in a pot. As it reaches the cooler outer regions, it sheds its heat, cools, and then sinks back down, creating enormous circulating currents. This continuous churning motion is vital for bringing energy closer to the surface. These massive convection currents are responsible for the granular appearance of the sun's surface, a pattern of bright rising cells surrounded by darker sinking lanes. Each of these granules is roughly the size of a small country on Earth, providing a visible testament to the turbulent processes occurring deep beneath. This constant upwelling and downwelling of plasma are not only efficient at transporting energy, but also play a crucial role in generating the sun's powerful magnetic field, which has profound implications for space weather and conditions across the solar system. The distinct differences in energy transport mechanisms between the radiative and convective zones highlight the incredible physics at play within our star. The radiative zone's density and temperature prevent convection, forcing energy to slowly radiate outwards. Conversely, the cooler, less dense plasma of the convective zone facilitates the bulk movement of matter. Each layer is perfectly adapted to its role, an intricate thermal machine designed to bring the fusion power from the sun's heart to its surface, ultimately warming our planet and sustaining life. Part 3. The Corona Mystery and Extreme Temperatures. Perched above the sun's visible surface, the photosphere, lies its ethereal outer atmosphere, the corona. This shimmering, pearly white halo is only visible to the naked eye during a total solar eclipse, an elusive spectacle that has long captivated observers. What truly mystifies scientists about the corona is its astonishing temperature. While the sun's surface itself is a scorching 500 degrees Celsius, the corona surrounding it inexplicably heats up to millions of degrees Celsius, sometimes exceeding 2 million degrees. This drastic temperature increase, moving away from the heat source, presents a profound paradox that continues to challenge solar physicists. Understanding this coronal heating mystery is one of the holy grails of solar physics. Scientists have proposed several theories to explain this phenomenon, none of which fully account for all observations. One leading hypothesis involves magnetic reconnection events. The sun's surface is permeated by powerful and constantly shifting magnetic fields. When these magnetic field lines become tangled and then suddenly snap and reconfigure, they release enormous amounts of energy, which could potentially heat the surrounding plasma to extreme temperatures, creating flares and other energetic events. Another compelling theory points to the role of waves, specifically alpha waves. These are a type of magnetohydrodynamic wave that can propagate through magnetized plasma. It is believed that these waves, generated by the turbulent motions within the convective zone beneath the sun's surface, travel upwards into the corona. As they propagate into the less dense corona, they gain amplitude and eventually dissipate their energy. dumping it into the coronal plasma and heating it to these observed million-degree temperatures. It's like shaking a rope vigorously. The energy travels along it and can be released at the end. The high temperature of the corona is crucial for the existence of the solar wind, a continuous stream of charged particles that flows outwards from the sun, filling the entire solar system. Without the immense heat, the sun's gravity would hold onto these particles more tightly, and they wouldn't achieve the escape velocity necessary to form this pervasive wind. Thus, the coronal heating mechanism is not just an academic curiosity. It's fundamental to understanding the environment of space and how the sun influences all the planets within its gravitational embrace. Studying the corona is exceptionally challenging due to its faintness compared to the brilliant disk of the sun. Advanced instruments like coronagraphs, which block out the sun's direct light, and space-based observatories such as the Solar and Heliospheric Observatory, SOHO, and the Parker Solar Probe, are indispensable tools. These missions provide unprecedented data, allowing scientists to peer into this enigmatic region and gather crucial clues that may one day fully unravel the long-standing mystery of the sun's million-degree crown. Part 4. Solar Cycles, Sunspots, and Hidden Rhythms. The sun, far from being a static ball of fire, exhibits a powerful and complex rhythm known as the solar cycle. This approximately 11-year cycle is characterized by a waxing and waning of solar activity, most visibly marked by the appearance and disappearance of sunspots on its surface. These dark, cooler regions are not merely cosmetic blemishes. They are windows into the sun's dynamic magnetic field, areas where intense magnetic flux erupts through the photosphere, temporarily suppressing the convection of heat from below and making them appear darker. At the beginning of a solar cycle, the sun is relatively quiet, with few sunspots. As the cycle progresses, the number of sunspots steadily increases, reaching a peak known as solar maximum. During this period, the sun is ablaze with activity. More sunspots, more intense solar flares, and more powerful coronal mass ejections. Following the maximum, the activity gradually subsides, leading to a solar minimum, where sunspots become scarce again before the next cycle begins, a continuous dance driven by the sun's internal dynamo. The underlying cause of the solar cycle is the sun's differential rotation and its intricate magnetic field. The sun rotates faster at its equator than at its poles, which stretches and twists the magnetic field lines. Over time, these magnetic field lines become increasingly tangled and concentrated, eventually popping through the surface to form sunspots. As the cycle progresses, the magnetic field reverses its polarity, meaning the north magnetic pole becomes the south and vice versa, completing the full magnetic cycle in about 22 years. Sunspots are often associated with intense magnetic loops that arc high above the sun's surface, sometimes spanning hundreds of thousands of kilometers. These loops trap plasma, causing it to glow brightly in ultraviolet and X-ray light, even though the sunspot itself appears dark in visible light. These complex magnetic structures are the breeding grounds for the most powerful solar phenomena, including the colossal solar flares and coronal mass ejections that can have profound impacts on Earth and space. Studying the solar cycle is vital for understanding space weather, as the sun's activity directly influences conditions in near-Earth space. Predicting the peaks and troughs of the solar cycle allows scientists to anticipate periods of increased solar storms, which can affect our technologies and infrastructure. The sun's hidden rhythm, a testament to its internal workings, governs the space environment we inhabit, making its careful observation a cornerstone of modern astrophysical research. Part 5. The Power of Solar Flares and Cosmic Explosions. Among the most spectacular and energetic events on the sun are solar flares, sudden, intense bursts of radiation that erupt from the solar atmosphere. These colossal explosions are fueled by the rapid release of magnetic energy stored in complex magnetic field structures, often associated with sunspots. In a matter of minutes, a solar flare can release as much energy as billions of megaton bombs, briefly outshining entire galaxies in X-ray wavelengths. They are the most powerful explosions in our solar system, a stark reminder of the sun's immense power. Solar flares primarily emit X-rays and extreme ultraviolet radiation, which travel at the speed of light, reaching Earth in about 8 minutes. Upon arrival, these high-energy photons can ionize the Earth's upper atmosphere, particularly the ionosphere, leading to immediate effects. They can cause shortwave radio blackouts, disrupting communication systems, and interfere with GPS signals. While the direct radiation itself doesn't typically reach the ground, its atmospheric interactions have tangible consequences for our technologically dependent society, highlighting the sun's far-reaching influence. Closely related to solar flares, and often occurring in conjunction with them, are coronal mass ejections, CMEs. Unlike flares, which are primarily bursts of radiation, CMEs are massive expulsions of plasma and magnetic field from the sun's corona into space. These colossal bubbles of superheated gas can contain billions of tons of matter and travel at speeds ranging from a few hundred to over 1,000 kilometers per second. If directed towards Earth, a CME can have even more significant impacts than a flare, as it carries both energy and matter. When a CME impacts Earth, it can trigger a geomagnetic storm, a disturbance in our planet's magnetosphere. The charged particles within the CME interact with Earth's magnetic field, causing it to oscillate and compress. This can induce strong electrical currents and power grids, potentially leading to widespread blackouts. It can also disrupt satellite operations, posing risks to communications, navigation, and even orbital safety. The most visible effect of a geomagnetic storm is the spectacular aurora borealis and australis, as charged particles collide with atmospheric gases. Understanding and predicting solar flares and CMEs is paramount for space weather forecasting. As humanity becomes increasingly reliant on space-based technology and vulnerable to disruptions, monitoring these powerful solar events is a critical endeavor. From protecting astronauts in orbit to safeguarding our ground-based infrastructure, studying these cosmic explosions allows us to better prepare for and mitigate the potential consequences of the sun's most violent outbursts, ensuring the resilience of our technological world. Part 6. Space Weather and Blackouts on Earth. Space weather refers to the conditions in space that can affect technological systems and human health. It is primarily driven by the sun's activity, particularly solar flares and coronal mass ejections, which unleash a torrent of energy and charged particles into the solar system. While the sun's warmth is essential for life, its more volatile emissions can pose significant threats to our increasingly interconnected and technology-dependent world, leading to a variety of disruptions, including potential blackouts on Earth. One of the most concerning impacts of severe space weather is its potential to induce geomagnetically induced currents, GICs, in long conductors on Earth, such as power grids and pipelines. When a powerful coronal mass ejection impacts Earth's magnetic field, it causes rapid fluctuations. These changing magnetic fields can generate electrical currents in these conductors, which can overload transformers in electrical substations. If enough transformers fail, it can lead to cascading power outages, resulting in widespread and prolonged blackouts. Beyond power grids, space weather also poses a significant threat to satellite operations. Satellites in Earth orbit are vulnerable to radiation damage from high-energy particles associated with solar storms. This radiation can cause temporary malfunctions, known as single-event upsets, or even permanent damage to sensitive electronics, shortening the lifespan of satellites. Communication satellites, navigation systems like GPS, and weather satellites are all susceptible, highlighting the widespread impact on services we rely on daily. Aviation, particularly polar flights, is also at risk during intense space weather events. High-energy particles can increase radiation exposure for passengers and crew at high altitudes, especially over the poles, where Earth's magnetic field offers less protection. Air traffic control and communication systems that rely on the ionosphere can also be disrupted, forcing airlines to reroute flights and incurring significant operational costs. This emphasizes the need for accurate and timely space weather forecasts to ensure safety. Protecting against the adverse effects of space weather requires a multifaceted approach, including robust shielding for satellites, resilient power grid designs, and advanced forecasting models. Scientists and engineers are constantly working to better understand solar phenomena and their terrestrial impacts. By improving our predictive capabilities and strengthening our infrastructure, we can mitigate the risks posed by the sun's dynamic nature, ensuring the continued functioning of our essential services in the face of unpredictable cosmic events. Part 7. The Parker Solar Probe and Missions to Touch the Sun. For centuries, the sun remained an untouchable enigma, its fiery embrace seemingly impenetrable. However, modern space exploration has defied these limits, with missions like NASA's Parker Solar Probe venturing closer to our star than any spacecraft before. Launched in 2018, the Parker Solar Probe is on an unprecedented journey to touch the sun, or more accurately, to fly directly through its outer atmosphere, the corona, to unravel some of the sun's most enduring mysteries, offering a truly revolutionary perspective on our star. The primary goals of the Parker Solar Probe are to trace the flow of energy that heats the sun's corona and accelerates the solar wind, and to understand the mechanisms that accelerate energetic particles. By flying within just 6.9 million kilometers of the sun's surface, a distance that is well inside the orbit of Mercury, the probe experiences temperatures up to 377 degrees Celsius and radiation levels hundreds of times greater than those experienced by Earth-orbiting satellites. This extreme environment necessitates cutting-edge thermal protection systems and robust engineering. The probe is equipped with a revolutionary 4.5-inch thick carbon composite heat shield, called the Thermal Protection System, TPS, which protects its instruments and systems from the intense heat and radiation. While the sun-facing side of the shield endures temperatures hot enough to melt steel, the instruments behind it operate at a comfortable room temperature. This ingenious design allows the probe to survive repeated passes through the sun's extreme environment, gathering invaluable data that would be impossible to obtain from Earth or more distant orbits. Among its many groundbreaking discoveries, the Parker Solar Probe has detected switchbacks, sudden, rapid reversals in the direction of the sun's magnetic field, which are believed to play a role in heating the corona and accelerating the solar wind. It has also provided the first direct measurements of the solar wind's acceleration region, giving scientists unprecedented insight into how this stream of charged particles is propelled across the solar system. These direct measurements are reshaping our understanding of fundamental solar processes. The mission is expected to continue its groundbreaking observations for several more years, making increasingly closer approaches to the sun. The data collected by the Parker Solar Probe, along with insights from other solar missions like the Solar Orbiter, is crucial for improving our space weather predictions and ultimately safeguarding our technology and astronauts. These missions represent humanity's boldest attempts to confront and comprehend the very heart of our solar system, pushing the boundaries of scientific exploration. Part 8. Myths of the Sun in Human Culture. Throughout human history, the sun has held a profound and multifaceted significance, inspiring awe, reverence, and countless myths across diverse cultures worldwide. Before the advent of scientific understanding, ancient civilizations often attributed the sun's daily appearance and disappearance, its life-giving warmth, and its sometimes destructive power to divine beings. These myths provided explanations for the natural world and shaped humanity's early understanding of its place in the cosmos, reflecting deep cultural connections to this celestial body. In ancient Egypt, the sun god Ra was one of the most important deities, often depicted as a man with a falcon head wearing a solar disk. Ra was believed to be the creator of everything, sailing across the sky in his solar bark during the day and journeying through the underworld at night, battling forces of chaos to ensure the sun's return. The daily cycle of the sun was a metaphor for creation, death, and rebirth, central to their beliefs about life and the afterlife, demonstrating a sophisticated cosmological view. The Greeks and Romans also revered the sun, with Helios, later identified with Apollo, driving his fiery chariot across the heavens. This powerful imagery not only explained the sun's movement, but also symbolized the god's strength and radiance. Many cultures viewed solar eclipses as ominous signs or battles between celestial entities, reflecting a universal human response to the dramatic and temporary disappearance of their life source, often leading to rituals and prayers to ensure its swift return. Among the Aztecs, the sun god Huitzilopochtli demanded sacrificial blood to maintain his strength and ensure the sun's daily journey across the sky. This belief underscored the vital role of the sun in their agricultural society and their understanding of cosmic balance, where human actions could directly influence the celestial order. These myths, though seemingly distant from modern scientific thought, were sophisticated attempts to impose order and meaning on a powerful and mysterious natural phenomenon, providing a framework for their societies. Even today, remnants of solar myths persist in language, traditions, and artistic expression. The sun remains a powerful symbol of light, life, energy, and renewal. While we now understand the sun as a star governed by physical laws, the deep cultural resonance forged over millennia continues to shape our perception of this celestial body. These ancient stories serve as a testament to humanity's enduring fascination with the sun, a star that has not only illuminated our world, but also our collective imagination. Part 9. The Sun's Aging and Red Giant Future. Our sun, like all stars, has a finite lifespan, a cosmic journey from birth to eventual demise, driven by the depletion of its nuclear fuel. Having spent approximately 4.6 billion years in its current stable phase, known as the main sequence, the sun is roughly halfway through this stage of its life. During this period, it efficiently converts hydrogen into helium in its core, maintaining a delicate balance between gravity's inward pull and the outward pressure of fusion. This stability has been crucial for the evolution of life on Earth. However, in about 5 billion years, the hydrogen fuel in the sun's core will begin to run out. As the core's hydrogen supply dwindles, the rate of fusion will decrease, leading to a slight gravitational collapse. This contraction will cause the core to heat up and become denser, igniting a shell of hydrogen fusion around the inert helium core. The increased energy output from this shell fusion will cause the sun's outer layers to dramatically expand and cool, transforming it into a red giant. This will be a monumental change, irrevocably altering our solar system. As a red giant, the sun's radius will swell enormously, potentially engulfing the orbits of Mercury and Venus, and possibly even Earth. The increased luminosity, despite the cooler surface temperature, would boil away Earth's oceans and strip its atmosphere, rendering the planet uninhabitable long before it is physically consumed. This dramatic expansion is driven by the sheer energy released from the hydrogen-fusing shell, pushing the outer layers outwards against the Sun's diminished gravitational hold, showcasing the immense power contained within its core. After its red giant phase, the Sun will undergo further transformations. The helium in its core will eventually ignite, fusing into carbon and oxygen, in a process known as the helium flash. This phase will be relatively brief, lasting only a few 100 million years. Once the helium is exhausted, the Sun will shed its outer layers, creating a beautiful and expanding planetary nebula, a celestial shroud of glowing gas and dust, illuminated by the dying star's core. This ejected material will enrich the interstellar medium, contributing to future star and planet formation. The remnant of the Sun will then be a white dwarf, a superdense core composed primarily of carbon and oxygen, about the size of Earth. Slowly over trillions of years, this white dwarf will cool and fade, eventually becoming a cold, dark black dwarf, a cosmic cinder in the vastness of space. This ultimate fate, though billions of years away, serves as a poignant reminder of the cyclical nature of the universe and the finite existence of even our most enduring celestial beacon, emphasizing the transient beauty of stars. Part 10. Can we harness unlimited solar power? The Sun, a colossal thermonuclear reactor in the sky, bathes Earth in an astonishing amount of energy every second. In just 1 hour, the sunlight that strikes our planet could theoretically meet the global energy demand for an entire year. This incredible statistic fuels the dream of harnessing unlimited solar power, envisioning a future where humanity's energy needs are met entirely by this ubiquitous, clean, and renewable resource, moving beyond finite fossil fuels. Currently, the primary method for converting solar energy into usable electricity is through photovoltaic PV cells, commonly known as solar panels. These devices utilize the photoelectric effect, where photons of light strike semiconductor materials, dislodging electrons and generating an electric current. Advances in materials science and manufacturing have led to increasingly efficient and affordable solar panels, driving a rapid expansion of solar power generation globally, transforming energy landscapes. However, unlimited solar power faces several practical challenges. One major hurdle is intermittency. Solar panels only generate electricity when the sun is shining. This necessitates robust energy storage solutions, such as advanced battery technologies, or large-scale grid infrastructure that can balance solar input with other power sources. Overcoming this storage challenge is critical for solar power to become a truly constant and reliable energy provider, especially in regions with fluctuating weather patterns. Another significant consideration is the sheer land area required for large-scale solar farms, particularly in densely populated regions. While individual rooftops offer decentralized solutions, utility-scale solar projects demand substantial acreage. Innovations like floating solar farms on bodies of water, or the integration of solar cells into building materials, are exploring ways to optimize space utilization. The efficiency of converting sunlight into electricity is also continuously improving, but there are theoretical limits to how much energy can be captured. Looking further ahead, scientists are exploring more ambitious concepts, such as space-based solar power. This involves deploying vast arrays of solar panels in Earth orbit, where they would receive uninterrupted sunlight, free from atmospheric interference or the day-night cycle. The captured energy would then be wirelessly transmitted to Earth, potentially via microwaves or lasers. While currently a highly complex and expensive endeavor, space-based solar power represents the ultimate aspiration for truly unlimited solar energy. a grand vision for humanity's future.